We are continuing in this chapter 4, and the next topic that comes up is the topic of precipitation. Do you remember from Chem 1, or were you ever exposed to this word? Do you know what the word precipitate means? And I don't mean like in the weather when we say there's precipitation. Xander, tell me.
In a chemical reaction, precipitate means like when you dissolve a liquid into a gas, and a liquid a solid is formed.
Okay. The key is solid is formed. A solid product. Well, the first part, not so much. Okay. The key is a solid product. Okay. Formation of a precipitate is when you have a solid product. Okay. That little S right there stands for solid. What do the AQs stand for? Aqueous. Okay. So, we get a solid formed, and ladies and gentlemen, this is what a precipitate reaction might look like. Now this may not look like solid material to you, okay, but what we would see is that if we let this reaction continue and let it sit for some time, you would see this sludgy material start to settle to the bottom of that beaker, and if we ran it through some filter paper, this material would catch on the filter paper and the rest of the material would run straight through, and you would see that it is actually a solid. Okay? Now, what I will be asking you to do today is I will be giving you reactants, and I will be asking you to predict the products. Now you had to do a little bit of that on our first test, and some of you, it was clear, were very uncomfortable with that. If you feel like you can't look at two reactants and predict the products, please come and see me sometime after school would probably be best, where we can sit down and figure this out. Okay, but I want you just to look at this reaction that's written out in yellow here. What type of reaction is this? Decomposition, single replacement, what type? What type? Meg, what type? Double replacement. Okay. The two metals have switched places, and we get two new products. And there's a purple arrow here pointing to this solid product, the precipitate, and it says insoluble. What does that word mean? Will not dissolve. Okay? That's why this one is the precipitate. Because when barium chromate is put into water, it just stays barium chromate. It does not dissolve like the other three do. Okay? And I want you to look at what this progression here. Alright, this is the same reaction I had on the previous slide. And I want you to notice these compounds that have AQ written after it, these are the ones that are soluble. If this one was insoluble, the other three must be soluble. What does the word soluble mean? Will dissolve. Okay? Well guys, what does it mean when an ionic compound dissolves? Literally, what is happening to it? It's breaking apart. Here's an even better word. This is like the $1 million word. It ionizes. Meaning, look from this row, this line, down to this line. And I apologize that I couldn't write this all out in one line. Potassium chromate is a soluble compound. Soluble means will dissolve, will ionize into its ions. Okay? That's what soluble means. Here's another one that is soluble. And it is ionized. How come I did not break this one apart? Because it's insoluble. It stays together. This one is soluble, I break it up. Okay, now, think back to like your first algebra class. Maybe even before that. If you have a fraction and you have something in the numerator and denominator that are identical, what can you do? Cancel them out. Okay? Well, guys, a chemical reaction is the same way. If you have something on either side of this arrow here that are two things that are identical, you can cross them out. What do you see? And again, I apologize, it's not all on one line. What can I cancel out here? All right, K plus. What else? NO3. Anything else? No? Okay. When you cancel those things out, this is what you're left with. And ladies and gentlemen, this is what is called a net ionic equation. Some of you did a little bit of net ionic equation writing in your Chem 1 class. Some of you have never seen this before at all. Okay? But before we go on to do some practice with this, I want to make sure you understand what it means when I cross these things out. It does not mean that they're not present. Okay? These ions are definitely present. If you think of this all happening in a beaker, those ions are definitely there. Okay? There is a name for these ones that you can cancel out. They are called spectator ions. Okay? And think about what it means to be a spectator, let's say at, a soccer game or something. If you're a spectator at a game, you are not participating in the game. You are there, but you're just watching it happen. Okay? These ions are present in the beaker. But are they taking place in the real reaction that's occurring? No, they're not. They're just floating around in the solution. These three things have names. This kind of equation, this is the kind of equation you have been writing since you were in Chem 1. Your most basic, reactants, products, not worrying about solubility. That's a molecular equation. When you split things up, when you ionize things that are soluble, but before you've canceled anything out, that is called a complete ionic, and this is the one that we are going to focus on, our net ionic. Okay? So he asked an excellent question. Am I going to tell you which ones are going to split and which ones are not? No, I am not going to tell you. So how are you supposed to know? Rules for solubility. Okay, now, first of all, there should be a book at every table, not a book for every single person, but at least one for 2 or 3 people. Go to page 144 in your textbook. Okay. Ladies and gentlemen, the chart that is on page 144 is just like this one. There's a list of rules to decide whether a compound is soluble or insoluble. Now you all should be jumping for joy because the fact that you have chosen to take AP Chem this year makes your lives much easier in some respects. From last year all the way back to like the 1960s, since this test was first being given out, people have had to memorize these. You be thankful that you don't. Okay? You are the first class to come through that does not have to memorize these. Does that mean that we're just not going to cover this? No. We are. But I don't expect you to have these things memorized. Okay? Now, the ones that are in green, you do have to memorize. Because I'll tell you guys, most compounds that you come across are going to be addressed by one of these two rules. If there's anything else, okay, I will give you those solubility rules. Now, let's just look at them for a second. Let me just, again, set the stage for how these are going to be used. I am going to give you questions in just a minute, and on our next test, where I give you the reactants in words. Not chemical symbols, words, and the reactants only. You will have to predict the products, and then using these rules, decide which compounds will split up, will ionize, and which ones will not, in order to get down to your net ionic equation. So, let's look at this. Any compound that has nitrate in it, and any salt that has acetate in it, is automatically soluble. If it says that something is soluble, should you split it up or keep it together? Split it up. Okay? Any compound that has an alkali metal in it, or ammonium, soluble. Okay? What do you think I mean by a halide salt? Halide, what does that sound like? Halogen, okay? Any salt, any ionic compound that has a halogen in it is going to be soluble. But there are some exceptions. Give me a halogen, any halogen you want. Fluorine, fine. Okay? Fluorine, a compound that has fluorine in it will be soluble unless it was something like AgF, silver fluoride, or lead fluoride. That would be an example of a compound that would be insoluble. If it's insoluble, do you split it or keep it together? Keep it together. Okay? Most of your sulfate salts are soluble. There are some exceptions, however. Most of your OH, hydroxide salts, are insoluble. Now pause right there for a second. If a compound has hydroxide in it, what's another name you could give it? We talked about this last class. Things that end in OH are bases. Okay? Bases. So another way to say this is, most bases are insoluble, except, now look what's in the parentheses. This should look familiar to you. What if I put these ions in a different order? Cabasser. Does that ring a bell? Bless you.
Thank you.
What are these things in this parentheses? We talked about it last class. Someone saying it? Your strong bases. People, what does it mean to be a strong base? It does not mean dangerous bases. What does it mean to be strong?
They completely ionize.
They completely ionize. Now think about that. We're drawing connections here, people. If strong means completely ionized, doesn't that sound like something soluble? Yes! Okay, good. You already know this rule. I should make you memorize these, because you already know them. But I won't. Make that clear. Okay? Number 6, sulfides, carbonates, chromates, phosphates. Most of those are going to be insoluble. Strong acids. Same situation, guys. Strong. Strong means will ionize. Do you remember the sentence I gave you to memorize your 6 strong acids? Imagine a perfectly clear, breezy summer night. Okay, now, question, ma'am. Thank you for bringing that up. In your textbook, there are cases where the chart will say something is slightly soluble. For our purposes, ladies and gentlemen, you may interpret slightly soluble to mean insoluble. Okay? Now, just as an example, I want you to look at this compound, lithium carbonate, Li2CO3. Look at our rules. Tell me, soluble or insoluble? Okay, she says soluble because it has a group 1 metal in it. Good argument. Who's got a different argument? Austin. Yeah. This rule says most carbonate salts are insoluble. We have conflicting information here. Okay? Wrong. It does not explode. Okay? The rule is lower number rules, meaning rules higher up, lower numbers like 1 and 2, supersede, overrule lower rules. Again, I can't stress enough how grateful you should feel that you don't have to memorize these, because not only did they have to memorize them, they had to memorize them in order. Yeah. You guys are lucky ducks. So, what's the verdict? Lithium carbonate, soluble or insoluble? Soluble. Okay? So, ladies and gentlemen, I'm going to walk you through the thought process here. Because on our next test, and in the problem set, you are going to have questions exactly like this, where I give you the reactants in words, and even though the directions say write the 3 types, really what I am asking you for is for the net ionic equation. So, I'm going to walk you through the thought process here. Here we go. Iron 3 sulfate and potassium sulfide. Alright? Could you please tell me what is the formula for iron 3 sulfate? Fe2. Okay. What is the formula for potassium sulfide? K2S. Okay. Now guys, for those of you that might be a little uncomfortable predicting your products, let me show you a little trick. Don't look at the chemical symbols here. Look at the words. If you switch these 2 words, tell me in words, what is one of my products? Okay, potassium sulfate. What's the formula for potassium sulfate? Okay. And in words, what is my other product? Iron 3 sulfide. What's the formula? Fe2S3. Okay. Folks, that is the first step in this process. is predicting your products. I think that's the hardest part of this process. Now what we're gonna do is go compound by compound and decide, is this gonna split apart? Is it soluble or insoluble? Let's start with iron 3 sulfate. Look at your rules. Tell me what you think.
Wait, don't we balance it first?
No, because remember the goal, thank you for asking. She said, shouldn't we balance it? If the goal is just to get to my net ionic, let's not even bother. Okay? Let's not bother to balance until we get down to the net ionic. What do you think? Back up your argument. Why do you say it's soluble? Okay, is iron sulfate one of those exceptions in the parentheses? No. Most sulfate salts are soluble, and this one is. Watch what I'm going to write. When something is soluble, that means it will ionize. That means write the ions. Fe with a +3 charge. Please notice I'm not even worrying about those subscripts. Don't even worry about them. All I care about is what is the ion coming out of this thing. Sulfate is the other ion. Okay? Next compound. Soluble or insoluble? Back up your argument. Why do you say it's soluble? Alright, it's got an alkali metal, but there's a rule further down that says sulfide salts are insoluble. Okay. That first rule supersedes the other one. So yes, it is soluble. What should I write for these ions? K plus and S minus 2. Pay no attention to those subscripts. They don't matter. How about potassium sulfate? Yes or no? For 2 reasons. It's got an alkali metal and a sulfate salt, or a sulfate ion. That gives it 2 reasons for being soluble. And the last one? Insoluble. Why do you say insoluble?
Because it's a sulfide salt and there is no alkali metal.
Right. It's a sulfide salt. Iron is not an alkali metal. There's nothing that iron has about it that's bailing that out, so this stays together. Please tell me what I can cancel out. Okay, sulfate. What else? When you cross an ion out, what kind of ions are those? Spectator ions. Okay. Can you all see? Just want to point this out to you. If all 4 compounds were found to be soluble and this one did not stay together, wouldn't everything cancel out? Yeah? You know what your answer would be if that happens? No reaction. If that ever happens, no reaction. If everything cancels out. That wasn't the case here. Is this balanced? No. Now let's worry about balancing when it's nice and simple. And ladies and gentlemen, that is my final answer. I want you to try numbers 2 and 3 on your own. Be careful, number 3 is a little tricky. Alright, ladies and gentlemen, I want to talk through this third one a little bit. Okay, numbers 1 and 2 were both, the first two were both what type of reaction? Yes, precipitation, but double displacement, decomposition, synthesis, what? Okay, double displacement, double replacement, however you want to call it. What is this third one? Single replacement. Okay? Now, if you will look, the products show which two elements have switched places. Cl and iodine. Ladies and gentlemen, if you're not sure when you're doing a single replacement reaction which elements to switch, okay, here's how you figure it out. Would you call chlorine a metal or a non-metal? Non-metal. Iodine is the non-metal that's in this compound. Like things always switch. A non-metal is always going to switch with another non-metal. Now folks, in a single replacement reaction, everybody listen. When you are ready to move down to this next line, I want you to notice that everything in the solubility rules applies to compounds only. Is that a compound? No, it is not. So you know what? You come across something that doesn't apply to our solubility rules at all. Do you know what you do on the next line? Just leave it as is. Don't do anything with it. Just leave it as Cl2. And move on. Now that is a compound. And this is a compound, which you'll need to look at your rules. But here's another pure element. Leave it alone. Solubility rules do not apply to pure elements. Okay? Continue. Now guys, you got to be careful. When you're thinking, okay, what can I cancel out? You can only cancel things out that are identical. What can I cancel out? Barium. Cl2 and Cl minus are not the same thing. So I've crossed out everything I can. Here's what I'm left with. Is it balanced? No. But now it's nice and simple to balance. Final answer. Okay. Single replacements tend to be more difficult for people than double for whatever reason. So I wanted to make sure to do an example of that. Okay. Now, ladies and gentlemen, Chapter 3 that we have now finished was all about stoichiometry. Okay? Tell me if this statement is correct or incorrect. You must have a balanced equation in order to do a stoichiometry problem. Correct or incorrect?
Correct.
Correct. Okay? Well, folks, this stoichiometry that we're about to do is no different. It is still just stoichiometry. There are a few little differences, but still, the stoichiometry itself is not going to be any different. Here is what is different, a little bit. Do you still need a balanced equation? Absolutely, yes you do. However, if you come across a problem where an ion is mentioned in the problem, like right here, the balanced equation that you want to use is not that full-out written one like you're used to doing from Chem 1. What do you think the equation is you want to work with? The net ionic equation. Okay? But guys, that's capitalized for a reason. The only time you must use a net ionic equation is if the problem mentions something about an individual ion. Just glance at number 2. Do you see anything about an individual ion? Me neither. So guess what? You still need a balanced equation, but it doesn't have to be a net ionic equation. You can just use that first one that you write out. But this one we do. And this is taken from an old AP exam, and the wording is a little bit tricky. So I'm going to talk through this one with you. It says, what volume of hydrochloric acid is needed to precipitate all of the silver ions from a certain amount of silver nitrate? Folks, they are giving you, I know it doesn't sound like it because the language is kind of strange. Here is one reactant. Here is the other reactant. This problem does mention an ion. I want you to take those two reactants. This is just more practice. Get down to the net ionic equation and then stop there. How come silver chloride is insoluble? I thought halogen salts were soluble.
Except for silver.
It's one of the exceptions. Again, the basic stoichiometry is going to be the same as you're used to. But in Chapter 4, and from now on, a lot of stoichiometry problems are going to give you that given starting information in some units that maybe you're not super familiar with. Like in Chapter 3, most of our starting values were given to us in grams. Okay? Let's look at this problem. It says, what volume of HCl, and then I'm given a molarity, is needed to blah, 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 and then I'm given some information about silver nitrate. Now guys, I want you to get used to seeing this combination, because you're going to see it a lot, where you're given a volume and a molarity of something. Now think about that for a second. If you have a molarity and a volume, what can you solve for? Okay, so in this case, moles of silver nitrate. Now, ladies and gentlemen, when you're using a net ionic equation as your main equation, you have to be very careful. Is AgNO3 in my net ionic equation? No, it is not. But what is AgNO3? What part of AgNO3 ended up? Okay. So, ladies and gentlemen, I'm just kind of plotting out a plan for how I want to do this problem. Okay? When you're using a net ionic equation, you've got to always ask yourself, is what's given to me actually in the equation I'm using? And if not, you need to get it there. So let's do that first. Alright? Let's calculate moles of AgNO3. Let's do that first. I'm given a molarity. Be careful with these units. Can I leave it in milliliters? Okay. Whoops. Bless you. How many liters is that? 0.05. Do the math. Okay, great. Now let's just go back and think about what we were thinking about a minute ago. AgNO3 is not in my net ionic equation. But you said that silver ion is, and I can turn this into moles of what's in my equation, moles of Ag plus. What I'm going to show you next, we did a little bit of this in chapter 3. Some of you did this in Chem 1, some of you did not. You've got to get it into units that you can work with. AgNO3 is not in my equation. Okay? Ladies and gentlemen, when you're doing this, taking an entire compound and breaking it down into its part, you always put a 1 in front of the compound. Can you please tell me how many silvers are in silver nitrate? 1. What if I were converting this to moles of O? What would I put here? There would be a 3. So just to be clear, all I have done here is taken my given information and put it in terms of something that I can work with. I haven't actually done any stoichiometry yet, believe it or not. Let me scroll back up. Let me repeat what I just said, because this is something that is new. All we have done, the math that is down here, all I have done is taken my given piece of information, converted it into units of something that is actually in my equation. Now let's figure out how to finish this problem. Look at the first phrase. What volume? Okay, I'm going to circle it. That is my unknown. That is my ultimate answer to this question. A volume. A volume of. I'm given a molarity. If I have a molarity, and I will ultimately be solving for a volume, what's missing? Okay? Moles of what? HCl. Now let's just pause for a second. Do you all agree, are we all in agreement, that if I can find moles of HCl and I'm given that molarity, that I can solve the problem? Are we all in agreement? You should be. If you have these two things, you can solve this problem. Is HCl in this equation? Yes or no? No. What did HCl turn into? Okay. I'm going to draw the arrow going the other way. I have moles of Ag plus at the moment. If I can get to moles of Cl minus, I can get to this, which means I can get to that. Listen, this is the only part of this problem where I'm actually doing stoichiometry, right here. And it's only one step. Here's my given. Stoichiometry means you're using that chemical equation that you have. Moles of one of the reactant to moles of the other. Can you please tell me, back from your Chem 1 days, if you're going from moles of one thing to moles of another in an equation, where are these numbers coming from? The coefficients. Yeah, the molar ratio. Don't even need a calculator for it. Ladies and gentlemen, we're almost finished. Here's where I am right now. If I now have moles of Cl minus, can I get to moles of HCl?
Yes.
Yes. We're doing the exact opposite of what we did right here. Instead of compound to part, I'm now going part to whole compound. And folks, please do not be deceived. These problems will not always have such nice 1 to 1 to 1 to 1 to 1 ratios. Part to whole. When you're doing that, which one always gets a 1 next to it? The compound or the part? Compound. How many chlorines are in HCl? Okay. So, ladies and gentlemen, I really would strongly advise that you map out a plan when you have a word problem like this, because you can always keep going back and saying, okay, now what do I do? Now what do I do? I've got moles of HCl and I have a molarity of HCl. Can I solve the problem now? Yes or no? Yes. Molarity equals moles over X. Folks, we will do the second one at the start of class on Wednesday.